Good morning, everyone. Hope you're all doing well. There was some confusion, probably my fault, on the labs that were due on Sunday. There was an additional lab to the nuclear chemistry lab on electrolytes. I just wanted to get you. I wanted you guys to get that done so that you didn't have to do it this Sunday over spring break. But I think a couple people missed it, and that's okay. I just extended the date to April 4th, which is the Sunday at the end of spring break. So you'll have actually 3 labs do that. And if you already did the electrolyte lab, don't worry about it. You don't, or if you did the electrolyte lab and you're like, oh my goodness, I totally did that wrong. It made no sense. You can go back and resubmit it if you want to. Okay. All that will be due the April 4th. So think of April 4th as the end of like a very, very long, refreshing weekend. If you have any questions for me, you definitely want to get those into me by Saturday. Sunday, I'm going on vacation with my family and I will be like away from email. So I won't be checking email and stuff. I will check when I get back. I want to say Sunday night, but that is Easter, so probably not until Monday. So just know that I will be, I'll be gone. Okay, let's get back into solutions. Lyric, what do you you need repeated? Why don't you just check in with me after class and we can go over anything you missed, okay? Okay, so we are looking at if you have a solution, right, and it has a given concentration, you can dilute those concentrations, and that means adding solution or solvent, or usually it's water, usually adding water, to lower the concentration of the solute. You do this with a can of canned orange juice. I've actually never made this before, but I guess you have a can and it's a highly concentrated orange syrup. And then you dilute it with 3 cans of water to get something that is digestible, right? Because this probably would be too sweet. So there is a simple calculation for diluting things. And let's see, wants to talk about more about what dilution is. So water is added, the volume of the solution will increase, the concentration then decreases, but the mass of the solute remains the same, right? So if we had 55 grams of salt dissolved in a liter of water, and then I doubled the amount of water, the solution becomes a larger volume. The concentration is decreased, but I still have 50 grams of the salt, right? The salt didn't disappear. It just was distributed over a larger volume. So here's the equations, pretty simple. C1V1 equals C2V2, or for molarity, M1V1 equals M2V2. But since molarity is a type of concentration, you could just stick with this. But what it's saying is that the initial concentration times the initial volume should always equal the final concentration times the final volume. Same thing with molarity. The initial molarity times the initial volume should equal the final molarity times the final volume. So when looking at these equations, we have 1, 2, 3, 4 variables. So you would be given 3 of the 4. I think the biggest difficulty with this is that people don't put the initials together and the finals together, okay? Make sure the initial volume and the initial concentration are together and the final concentration and final volume are together. If you want to give yourself a little note, this is always the initial. This is always a high concentration. And a lower volume. And then at the end, it's always a lower concentration with a higher volume. When you dilute something, you go from a high to a low concentration. You can't dilute something to a higher concentration. So as far as running a calculation with this, prepare a table with the values, rearrange the equation to get the unknown quantity, and then plug it in. So right here, what is the final concentration when you have 0.50 liters of a 6 molar HCl solution that is diluted to a final volume of 1 liter? And we want to figure out the final concentration, right? So we are trying to find C2, ending concentration. We have the initial concentration, which is 6 molar. We have the initial volume, which is 0.5, and we have the final volume, which is a liter. So what are we doing with the volume here? The volume is increasing, right? It's actually doubling. The volume's doubling. So if the volume's doubling, I would expect the concentration is going to get cut in half. That's how that equation works, is one goes up, the other goes down. Let's plug it into the equation though and make sure. So here is our M1V1 equals M2V2. We want to solve for the final concentration, the M2. So M2 equals M1 V1 divided by V2. Where did that come from? They just isolated the variable. So you take, if we want to get V2 over here, I divide each side by V2, right? This cancels out and I'll be left with just M2, which is the thing that I'm solving for. So M2 will equal the 6 molar times the fraction of the liter change, 0.5 divided by 1, which gives us 3. So when the volume, in this case, the volume doubled, the concentration would get cut in half. If the volume tripled, the concentration would get cut by a third, you would expect, or cut to a third. So I'll have you guys do one of these. What volume of a 2% mole volume HCl solution can be prepared by diluting 25 milliliters of a 14% mass volume HCl solution? So this is same equation. The only difference is that the concentration is being given to you as mass volume, but you can use it the same way. You don't have to change it. You can just use the 2% as 2, and you can use the 14% as 14. Okay, so I hope that these aren't seeming too scary. You'll know you want to use the dilution when it says, hey, I'm diluting something. So just write out M1V1 equals M2V2. You're given 3 pieces of information. You want to solve for the 4th. The hardest thing is coupling what you need with like the initials and the finals. So you're starting with an initial volume of 25 milliliters. You're starting with a percentage of 14. You're ending with a percentage of 2. So we're cutting or we're diluting it by a factor of 7, right? 14 divided by 2 would be 7. So I would expect that my volume is going to go up by a factor of 7. So here's our information. If C decreases, concentration decreases, volume should increase, right? And we take our 25 milliliters, we multiply it by the 14 and divide it by the 2, and we get 175 milliliters. Is that consistent with what we know about dilution? Yeah, as we dilute, the concentration goes down, the volume should go up. Okay. Questions on that? Pretty straightforward. Why don't we do one more just to really get it in there. So I'll give you all just 2 minutes for this one. Okay, so this one is asking, what is your final concentration if you take a 9% NaOH solution and you dilute it from 10 milliliters to 60 milliliters. So hopefully you're starting to see a pattern. What's happening to the volume? The volume is increasing by a factor of 6. So we would expect our concentration to decrease by a factor of 6, right? So volume increases, concentration should decrease. We plug it in, 9 times the 10 divided by the 6, right? Decreasing by a factor of 6. So 1.50 is our final concentration. Oh, yeah, I think we're good. Okay, I think we're good. Anyone who took Chem 092, took it with me or took it at AV Tech, you guys remember solution stoichiometry and how, or just remember that it was very involved where you had to go from volume of one thing into moles and then moles back into volume. And it was like, yeah, we're not going to do it for this class. Woohoo! So you just have to do solution dilution. Okay, you can leave solution stoichiometry in the past for right now. So let's get into properties of solutions. This is something that's a little bit new, but you do need to understand. So over here they have an IV bag, and this is 0.9% NaCl solution, and it is said to be isotonic. Isotonic means that the concentration of the IV bag is the same or similar to the concentration of the blood in the cells of the body. So in reference to solutions, solutions in general are transparent. They don't separate, right? So if I have a solution of salt water, like that IV bag, the salt's not gonna fall out of solution, it stays suspended. It contains small particles, ions, or molecules that can't be filtered out through a semi-permeable membrane. So our solutions, we kind of think of those as like really tiny, small things that we can't separate out with this semi-permeable membrane. Colloids are something that are a little bit bigger. They have medium-sized particles in them. They can't be filtered, but they can be separated by a semi-permeable membrane. So if we have some sort of semi-permeable membrane, colloids can't get through, but the solution ions and particles would be able to get through. Here are some examples of what we would classify as a colloid. So fog, clouds, hairspray, dust and smoke, shaving cream, whipped cream, styrofoam, marshmallows, mayonnaise, cheese, butter, blood plasma. So they're like solutions, sort of, in that there's like a homogeneous mixing of the thing, but they are a little bit clunkier in what's being dissolved. So it's easier to separate out that. Then we have the biggest of these clunky things. So we have solutions, colloids, and then suspensions. Suspensions are heterogeneous, non-uniform mixtures. These are very large particles that eventually can settle out of solution. They can be filtered, and they must be stirred, or you need it to be agitated in order for them to stay suspended. So things like this include blood platelets, muddy water, calamine lotion. If you ever used calamine lotion for mosquito bite, right, you got to shake it because part of the active ingredient settles to the bottom. Same thing happens with platelets. And then you can see that with muddy water, right? After a really big rain, the French broad will kind of change color and turn really muddy because it's stirring up all the fine grain stuff at the bottom of the river. Are oil and vinegar a suspension? Yeah, I guess you could call that a suspension. Yeah, it'll eventually settle out. Yeah, because it's not dissolving in the material, right? The oil is definitely not going to dissolve in the water. So here are a bunch of all that information together on one table. So solution, our most fine grain thing, colloid, and then suspension. If I had all three of these mixed together, solutions, colloids, and suspensions, I could get the suspended stuff out just by putting it in a container and letting the suspension settle, right? I could get the suspension and maybe some of a couple colloids, but not a whole lot, through filter paper. But really I could get the filter paper, or I could get the colloids out by using a semi-permeable membrane where the solution is able to move in and out, but the bigger things are left behind. So let's see, study check here. A mixture that has a solution, a solute particles that do not settle out but are too large to pass through a semi-permeable membrane, that would be a colloid, right? So that's that middle spot where It won't settle, but it can't get through the semi-permeable membrane. So let's talk about osmosis. In osmosis, water, which is the solvent, if it isn't water, it would be the solvent. But we're going to be talking about it with water. Water flows will always flow from a lower to a higher concentration solute. So if I have this semi-permeable membrane, and this specific semi-permeable membrane won't let the particles through. This is like sugar or whatever. I've got water on both sides. This is a low concentration though, and this is a higher concentration. This water is going to flow from the left side over to the right side. There's going to be a natural pull of the water in this direction. So water or the solvent will always flow from lower to higher solute concentration. It's kind of like it's trying to balance out the concentrations, right? If this is a low concentration and this is a high concentration, it's going to want to move to the higher concentration until it's equaled its concentration. So what will actually happen is the height of the water here will drop and the height of the water on this side will increase, or the volume will increase. This will continue to happen, the concentrations, until the two concentrations are equal to each other. So you may have heard of something called osmotic pressure. Osmotic pressure is equal to the pressure that would prevent the flow of additional water into the more concentrated solution. Greater as the number of dissolved particles in the solution is increased. So water naturally wants to flow from here to here, right? There is a resistance or a pressure that I would need to apply to keep that water from flowing. The amount of pressure or force that I would need to use to prevent the water from flowing over is known as osmotic pressure. If you've heard of reverse osmosis, specifically with like water purification, reverse osmosis is when the osmotic pressure that you're applying the pressure that you're applying is greater than the osmotic pressure. And so you can force a salty solution or a concentrated solution into a more purified version. So what will actually happen is you reverse the flow. So I take the water that's over here and I force it through the membrane. It will leave the particles behind and you'll have just pure water. And so that's kind of what's happening when they reverse osmosis for salt water. Over here, you've got a bunch of salty water. You've got pure water on the other side. You force the water through the membrane, you leave the salt behind, and now you've got a bunch of pure water. It's like, oh my gosh, all the answers to our water shortages right there in reverse osmosis. Well, osmotic pressure is super high. Like it requires a lot of energy. So if you were trying to desalinate water by this process, you would have to use a lot of energy. What sort of energy do we have available to us pretty readily? Fossil fuels. So reverse osmosis is something that happens, or desalination through reverse osmosis really happens in areas where they have a lot of fossil fuels, like the Middle East. We haven't found another way that's super sustainable. Maybe if we could attach it to a nuclear power plant that has a bunch of nuclear additional quote unquote waste, but still energy that we could use for it. So, so we've got this idea of osmosis, right? Things are always going to want to move from higher, or water is going to want to move from lower concentration to higher concentration. It's trying to dilute, okay? So the water is going to move from the low concentrated area to the high concentrated area. So if I have an isotonic solution, like we were talking about earlier, that 0.9, and you do want to know these numbers, okay? Know that for blood, 0.90 NaCl is isotonic and 5% glucose is isotonic. Okay, you do want to know those numbers. That means that the solution and the blood, the red blood cell are in equilibrium, or they're balanced, right? The solution outside and the solution within the blood cell are at the same concentrations. So the exchange of water, there is water moving through it and it's equal and opposite, right? So water is moving into the blood cell and water is moving out of the blood cell. So the blood cell will remain neutral, right? It's going to stay in its natural state. It's not going to get puffy or shrink down. It's nice and happy. So that's why they use isotonic solutions, right? You never want to give somebody a solution, like a homemade solution of salt that has like a super high concentration of salt, okay? Because you'll dry the person out. So let's actually look at that. What if we were in what's known as a hypertonic solution? So hypertonic, hyper meaning over, right? Hyperactive, hyperglycemic, over. So a hypertonic solution is a solution that has a very high concentration. So now let's look at this over here. We've got a solution and the solution is high relative to the red blood cell. The red blood cell is low. So how does the water want to flow? Well, water always wants to flow from low to high. So water is going to be flowing out of the cell into the solution. It's like your little blood cells are trying to dilute the solution around you because it's so concentrated. This is why you don't want to inject a high salt concentration into your body, because the cell will undergo what's known as crenation, which is where the cell will shrink as it leaves it. It can then, obviously damage the red blood cell. So that's not a good thing. Okay, we've got dialysis. In dialysis, a solvent and a small solute particle passes through an artificial membrane. Large particles remain inside. Waste particles such as urea from blood are removed using an artificial kidney. So this is dialysis. This is a process of, like, your kidneys act as this semi-permeable membrane to remove bigger like toxic things that we don't want in our system. When your kidneys start to fail, you need to do that artificially. So, I mean, this is not what a dialysis machine looks like, but it's sort of similar to that, where it will take the material, the blood in your system, it'll run it through a semi-permeable membrane. The blood can pass right through. The bigger things will get trapped. Okay, I don't know why. Oh, I must have just skipped it. Okay, I skipped hypotonic. I was wondering where that went. So we did hypertonic already. Let's jump back to the slide, hypotonic. So hypo means under, right? Hypoglycemic. So a hypotonic solution has a lower concentration than the blood cell. This is also not a great thing for your blood cells as well. So you would know, like a really good example of a very, very low solution would be just pure water. You would never want to inject pure water into your bloodstream. Why? Well, think about what happens with the cell. So if you have a low concentration on the outside and you have a very high concentrate, well, it's not very high, but it's high relative to the solution, right? A high concentration within the cell, how is the water going to flow? Remember, water always flows from low to high concentration. So the water is going to flow into the cell. And so now you've got this process called hemolysis, which is where the blood cell expands, it swells, and sometimes the blood cells can actually burst, right? And a bursted blood cell is no good. So you want to find that solution, at least with blood cells, that is isotonic. That's right in that sweet spot where the water flowing in and the water flowing out is equal. Unless you're already experiencing something like crenation, then they could, give you a slightly different solution to balance that out. Okay, so here are some different solutions. I want you to tell me whether the solution is isotonic, hypotonic, or hypertonic with blood cells, okay? So a 2% NaCl solution, a 1% glucose solution, a 0.5% NaCl solution, and then a 5% glucose solution. Okay, so let's remember what our isotonics are. We said 5% glucose, right? And 0.9%, not 9%, 0.9% NaCl. So do any of these match up with that? Yeah, actually this one matches up with the glucose, right? 5% glucose. So we could say that that's isotonic. It's the same concentration. So what would happen to the blood cells? Nothing. They're kind of content with that. Let's go back to the first one, 2% NaCl. That is way more than the 0.9% that we desire. So we're going to say that that is hypertonic. What happens with hypertonic solutions? This is really, really concentrated, right? So what is it going to do to the blood cell? If it's really concentrated, remember, water wants to flow from low to high. So this is going to suck the water out of your blood cells, or you're going to get crenation. 1% glucose. All right, that is lower than what we like for glucose. So that's hypotonic B. This is going to be a system, or this is going to be hemolysis for the blood cell, right? The blood cell is more concentrated than the solution that it's sitting in. So the cell is going to suck up water from the surrounding solution, and we could get hemolysis or bursting. Then this last one here, 0.5 NaCl in relationship to NaCl. This is also hypo, this is under. So we would expect to see hemolysis with that as well. Okay, so I want you to tell me when placed in each of the following types of solutions, what would happen to the red blood cell? And so if it helps you to decide if it's hypo, iso, or hyper first, do that. But you've got a couple different solutions here. Is the cell going to remain the same? Is it going to undergo hemolysis? That's expansion, or is it going to undergo crenation, which is when it shrinks? And if it helps to draw a little picture, like a blood cell with water around it, and then you can put some arrows in, sometimes that helps to clear up if there's any confusion. All right, so 5% glucose, that's our happy spot, right? That's our isotonic. So what happens to our cells whenever we're isotonic? Nothing. So this would be an easy A. All right, glucose. So I'm gonna draw a little picture over here with a blood cell, and we've got, a water solution. So the solution is 1%. Blood cell is always going to, for glucose, it's always going to be at 5%, or that's where it usually sits at. So 5% and 1%. Water is always going to flow from lower concentrations to higher concentrations. In this case, water is going to flow into the blood cell. Okay. If water is flowing into the blood cell is going to expand or swell. This would be hemolysis. You guys seeing how that works? Sometimes I see a lot of times people get it reversed. So just make sure you figured out, what direction is everything going. So we've got B here. All right, what's our next one? We've got a 0.5% NaCl. This likes to be at 0.9% for NaCl. So water is going to move from lower to higher. So we're going to move into the cell for this one. If we're moving into the cell, we're going to expand the cell. This is also hemolysis. Last one here, we've got 2% NaCl. Salty, salty, salty solution. What, conceptually, what would you think if you had a really salty solution? It would probably dry you out, right? That's what's happening with the cells here. Here's our lower concentration, 0.9. Here's our higher concentration of 2. Water is going to flow out. It's going to dry the cell out. This is going to be crenation. You do get a little bit of practice of that on your labs. You probably will see a question about that. So just remember the two numbers, the 0.9 and the 5%, or have them on your formula sheet somewhere. Okay, that is it for solutions, and that is it on my part for today. So have a really great spring break. Yay! Let me know if you have any individual questions. I'd be happy to help you out. Otherwise, I will see you on Monday. Again, I'll be in email communication through Saturday evening. Maybe I'll do a last check Sunday morning. So hit me up when we come back. Cool. All right, everybody. Bye. Have a nice break. Sparrow, when will the mastering chemistry grades be in Moodle? Oh, right. I need to do that. So unfortunately, the mastering chemistry grades the Moodle isn't tied into the mastering chemistry, so I have to manually plug them in, and I just dread that. So I will try and do that. I'll try and get it, some of them done by tomorrow, Sparrow, okay? Because I do need to do that, yes. Yes, it is one of the few things that, I just can't stand doing, but it needs to get done. So yes, I will try and get that to you guys tomorrow.